Hi, my name is Peter Ditlevsen. I'm professor at the Niels Bohr Institute, and I work in the field of many things: chaos, complexity, turbulence, and climate dynamics. And what I am going to tell you about, and as I understand it without formula, is how the climate works, and that we'll see how that goes. And climate is a field of science in which there are probably as many disagreements as in cocktails, and there are disagreements on many different levels. There's sort of the disagreement in the sense of sort of the deniers, the flat earthers, saying that we do not believe this and that. That's from a scientific point of view not very interesting. That people have views like that. I mean, our understanding is based on solid knowledge of greenhouse effect and everything that we know, but we're asking questions that are further, questions that are sort of at the edge of what can really be known, where we don't even know if we can know these things. And the first thing that's of concern is, of course, that we have observed that the atmospheric content of carbon dioxide, which is a greenhouse gas, and I'll explain this in a short while, what this is increasing in the atmosphere. And that's been known for 100 years. It's been measured since 1957. 1957 was the UN geophysics year. And that year, a lot of measurements were launched. So we have temperature measurements from the ocean. We have this measurement of this carbon dioxide in the atmosphere, which was taken far away from any industry in Hawaii, in an astronomical observatory high in the atmosphere, far away. So this is really a signal of the global content of carbon dioxide. And you see very nice annual cycles, and that's really the biology sucking up CO2 and releasing CO2 in the winter. And then you say, how can that be? This is a global signal, but that shows that there's just more biology, more leaves, more land on the northern hemisphere. So this is really a signal of the northern hemisphere, summer and winter, you see in this curve. Now, it's been discussed for 100 years if this really is so much that this would influence the climate of the planet. And the big climate puzzle has really been to understand why is the climate changing? Why would there be ice ages? Because in the previous century, in the 1800s, 1830s and so on, people started realizing that things in the geology was such that it could not really be explained. Say why there would be big boulders in Denmark, and you can take these boulders and see they come from the mountains in Norway, and how would they be transported here? And sort of the saying would be, that's the big flood and from the time of Noah and things like that. That's of course never been sort of taken seriously by scientists. Not 100 years ago and not 200 years ago at all. But this was a puzzle, and it was solved by a glaciologist, a Swiss glaciologist, Agassiz, who studied the glaciers of the Alps and saw that they would really be pushing rocks and everything, moraines, and making landscapes that you now see. That's how Denmark is formed, and you see it in Scotland and many places. So they know that this place has been covered with ice. So this was the big climatic mystery for 100 years. How can that be? How do we explain that? So this is not a talk about ice ages, but I can tell you now that this puzzle is only partially solved. We do not, our models that I will talk about later, are not capable of doing it yet. So sort of the next biggest puzzle is to know, is our influence on the planet such that it can really change climate? This is the worry, and this was proposed already 100 years ago and calculated by a Swiss chemist Svante Arrhenius, who looked into the atmosphere and made some estimates on the absorption and so on, which I'll return to, and came up with the result that if you doubled the carbon dioxide, we would have an increase in temperature of a few degrees, which would be very nice. He was sweet. I mean, I think that would be, we should do that. But of course, it's been discussed later, if this is the case, and will start being a worry. UN set down this panel that you all heard about, the IPCC panel, that was an intergovernmental panel on climate change, which should gather all the information to answer the question if climate was changing due to our anthropogenic emission of carbon dioxide. And there's been a report every 5 or 6 years, and the conclusions have been more and more sort of certainty that we do actually change climate. In this, you see, in 1995, the balance of evidence suggests a discernible human influence on global climate. And you can imagine them sitting at these nice tables with politicians, breathing in their necks, saying take it easy. So they're very careful. In 2001, there's new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activity. So that's sort of stepping up. And the last report here, which was sort of the warm-up for the COP15, is most of the observed increase in globally average temperature since the mid-1920s 20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. So, and probably they've known this all along, but politics sort of turned. The Al Gore effect's been that we can. This is a serious problem. Even people tied to industry takes this seriously. And this is. I'm just showing this curve to show the last part that I previously showed here is this increase here. So this is actually an unprecedented increase in carbon dioxide over a period of 500,000 years or 600,000 years. This is sort of the curve that I don't know if you saw Al Gore's film, but he'd have this curve all over the stage. You'd go over here, and then he'd have an escalator, and he would sort of be standing on the escalator and going up, and then he'd be pointing to this point here and say, "This is very, very dramatic." Of course, it's a huge increase in carbon dioxide, but if you look at this is a proxy for temperature. You see these wiggles here, they are ice ages. And ice ages are huge changes in temperature. Of global change of temperature of perhaps 5 degrees. Okay? And this is what you sort of see here. But there's this little mystery here that we did not increase here 5 degrees yet. So there's more to it than carbon dioxide. But the kind of temperature change we're looking at here is probably of the same order as an ice age, going the other direction, of course, from that. So what is the physics behind that? How do we answer a question, how much will the surface temperature increase with the doubling of atmospheric CO2? Let's just look at the very basics of that. And this is the very basics. This is how much physics probably I will do. Now, this is the different components of the atmosphere, different molecules. And the reason that we do have a greenhouse effect is that molecules, they absorb the incoming and the outgoing radiation in the atmosphere. And that's where it all lies. And this absorption depends on the energy of the light coming in and out. Now, if you look here at the incoming light and the outgoing light, that we all understand very well from physics. If you look at the wavelength here, high energy is up here. This is short wavelength. This is the solar influx. This amount of light in these wavebands come from the sun into the atmosphere. This goes out from the Earth. This is what's called black body radiation. Now, Sun is very close to being a black body, which is sort of bad naming from physics, but this is what's called the equilibrium. Will always be most probable radiation coming out of the Sun. The Sun is about 6,000 Kelvin on the surface, and this is the radiation you'd get from that. This is the radiation from Earth. Earth is about 300 Kelvin or 20 degrees C, and this is the radiation you get out of the Earth. And the difference between these two is everything. So we have, is there chalk? Oh, it's here, yeah, sure. Oh, all kinds of colors. I'll do the white here. So what we're talking about is the Sun, the Earth, and space. The Sun is 6,000 degrees. Usually we use the Kelvin scale. I guess that's from absolute zero. That's minus 200. So 0K is minus 273 Celsius. That you probably all know. But anyway, Earth is around 300. So you have a hot place and a cold place, and you have an even colder place here, which is the universe. That's only 3 degrees above absolute zero. Now that's important, because what physics tells you is that heat goes from hot places to cold places, right? You have a house and it's cold outside, the heat will escape to outside. That's the way it goes, okay? Which means that heat is escaping from the Sun, it hits the Earth, and the Earth is escaping to space, because space is a very cold place. Now, all we need to know then is, how much will Earth then be heated in this content. Now we know how much is coming in from the Sun. That should just balance what's going out to space. So that's sort of an easy calculation. Okay? So we would say that the incoming, what's going in here, the incoming radiation should balance the outgoing radiation like that. Okay? If that's not the case, temperature will change. So we'll say that change of temperature, we write that in a sort of a strange way, delta T divided by time. So this is the change of temperature here, would be the imbalance between these two. So that's the first climate equation that we'd have. Okay. Now we could calculate, of course, we know what this is. So this should be the same. If temperature doesn't change, it should be the same. We can calculate that, and that would be 30 degrees colder than we have now. We actually have the Earth covered with ice. So the reason we don't have the Earth covered with ice is that we have a greenhouse effect. So we should be happy about the atmosphere. So what does the atmosphere do? Well, we have to look at this strange curve then. What happens here is we show for all the different molecules in the atmosphere, oxygen there's a lot of oxygen, there's a lot of nitrogen, but we also have carbon dioxide and we have water vapor. And these are the two most important greenhouse gases. Now, every time you see something high here, this means that if I radiate, I have a flashlight into the atmosphere, it's absorbed here at this wavelength. Okay? At this neighboring wavelength, it's not absorbed here. So that's the whole physics. Now, if you look at exactly this wavelength here, this is where the Sun is shining. This is visible light. This waveband is actually visible light. There's nothing in the atmosphere that absorbs. There's a little bit there. This is the ozone. Fortunately, ozone is also taking this very high energy. This is what gives you cancer. And ozone is eating that, fortunately. So we should be happy about ozone. But here, all this shines through, which means that in this waveband, the atmosphere is transparent. So if we look at the atmosphere here, this is the ground, this is the atmosphere, the Sun is up here, it shines all the way down to the ground. So this is exactly the wavelength where we look, right? We know that because you just go out at night and you look out and you see faint stars, which means that it's very, very transparent. Isn't that a coincidence? course not, because our eyes are, of course, adapted to seeing in the atmosphere, right? If the atmosphere was like a fog, we'd be eaten by, somebody bigger than us that could see better or smell better. So we have, of course, adapted our eyes to exactly this band here. So the atmosphere tells us how that is. Now, Earth has to radiate back exactly the same amount here, else it would be heated, right, or cooled. Now it's radiating at a different temperature, which means that it's radiating here. So now it's sending the energy back. But now you see here, there's a lot of absorption here. Carbon dioxide is absorbing all this. Water vapor is absorbing all that. Okay, which means that if you're sitting out here, now we were sitting down here looking with our eyes up, we could see the stars, so we could see the sunlight. Now we're sitting up here looking down. The atmosphere is opaque. Okay, the atmosphere is opaque, which means that it's like a fog at that wavelength. Okay, so what happens then? Well, we can see into the fog. I mean, that's you know that from all the old, Frankenstein and so on. You get this character coming out of the fog, and it's like 10 meters. So that's the optical depth of the fog. You walk into the fog, and then you're gone. So what we can see is down to this level here in the atmosphere. I cannot see down there. Here, sort of this Dracula becomes visible, and now out here, now he's very close. Okay. What does that mean? That means that what I am seeing here is the radiation out of this level here. So it's the radiation out of this level that tells me how this should look. Now, there's a very general physical law that tells me what will the radiation be from there. This would be a formula which has a constant. Here it's just a Greek symbol, sigma, Stefan-Boltzmann constant it's called, times the temperature at this level here to the fourth power. It doesn't matter how that is, but that is very fundamental. And we know that from physics, this is just a formula. It's a law of physics that this is the way. But this temperature here is really what should balance here. So the incoming should be equal to that here. But now, what I told you before was that this temperature here is really 30 degrees colder. But this is the temperature up in the atmosphere. So I know now that at this level the temperature has to be this. So what's the temperature at ground? Now that's easy, because that just has to do with how the structure of the atmosphere is. And you all know, you've all been flying. And when you fly, they have tell you how fast you fly, and they also tell you the outside temperature. And that's decreasing with height. Actually decreases it somewhere between 7 and 10 degrees per kilometer, right? So if I now make a sort of temperature axis here, temperature, I can draw the temperature like that. And actually it does something like that further up. That's a different story I can come back to. Okay, so this one drops about 10 degrees per kilometer. Now, all I have to do is go outside, look down and see how far in can I see at that wave band. And I can see down to about 3 kilometers above the ground, which means that this temperature has to balance the incoming radiation. And this difference here, that's the greenhouse effect. That's the natural greenhouse effect. And this here is 30 degrees, or actually 32 degrees Kelvin. Okay. So if we didn't have an atmosphere, it would be 32 degrees colder here, which is, it's not. Okay, now we know what happens with anthropogenic greenhouse gases. Now we put in more gas into the atmosphere. What does that mean? It means it becomes foggier, right? It just becomes foggier because I put in more of the fog, which is the CO2. This means that I cannot see. Here Dracula is invisible. Here I see him again, right? Now this temperature, this level, which is the effective level I can see, needs to have that head temperature now. So what happens is, of course, that, anything disregarded, the temperature has to do this instead, right? Which means that the temperature at ground becomes larger here. This is the anthropogenic. If this is 3 kilometers here, and if I increase this with an amount, this is about a few degrees. That would be sort of a back of the envelope. The reason that this is increasing here, that's due to the ozone. The ozone is absorbing exactly here, and this is what heats the upper atmosphere. That's the stratosphere. This is stratified, and this is the lower. This is an important picture for the volcano that's going on now, and we might talk about in a short while. So this is the greenhouse effect. That's the important thing here. Now, there are lots of things in there. Now, if you really want to model this, this is what comes in, and what goes out is the same. So you take these two numbers and you add them up. This is what comes in. This is the average incoming solar radiation, okay? Which is 342 watts per square meter on average in the globe. Which means that you have a square meter here, and then you put, they don't exist anymore, but if you had them, you'd have 3 lights, 100 watts, and 1 40-watt lamp in 1 square meter. That's about what the sun gives us. Okay? Of course, it's more at the equator, less in the pole, and this and that. Now, some of it is just reflected. A third of that is just reflected right out of here, which means that it hits clouds, and then it's reflected. Clouds are white, so they just reflect in the visible. The ground reflects in the visible. A third is going out. Okay, so it's really not what comes from the sun, but it's 2/3 of what comes from the sun that should balance. Now, there are lots of other things. You have evaporation, and evaporation leaves heat in there, so that's a way of transporting heat. And then you have this radiation that comes in here, which is what I drew over there. But from the atmosphere, which is opaque, it radiates back here. So there's a lot of complications in there, and this is really what we want the details of. If you have more clouds, you'll have more back radiation, you have more reflection, and this and that. So you have two big numbers that change things in this balance. If you look at now, this is actually the same equation I put up. This is what comes in from the sun here. And 1 minus what is reflected should balance what comes in. Now, I wrote this in a little different way from there. I just take this to be the ground temperature and this to be the greenhouse warming. Let's just look at the different planets then. Now, of course, the incoming radiation is easy to calculate because that just goes with the distance to the sun. 1 divided by the square of the distance to the sun. That's quite easy because it's the same radiation that goes out through all spheres away from the sun. So you just look at the surface of the sphere, right? And the surface of the sphere, that's, what is that? 4 pi r squared. That you know from school, okay? Anyway, so there's a curve. The further away you get from the sun, the less radiation. So if you have a planet out here, we have a planet further out, that's Mars. It gets less radiation. We have a planet in here, that's Venus. It gets more radiation. So we could just calculate what should be the temperature on these planets. It should just fall on this one here if the greenhouse effect was the same as on Mars. Now you see Earth is actually warmer than it should be. This is the greenhouse effect of Mars. But if you look at Venus, Venus is extreme. Venus is much, much warmer. So it has an extreme greenhouse effect. And it's even more extreme than this due to the fact that actually the reflection from Venus is also larger. So that's a really, really strange planet here. So if we just change one of these parameters a little bit, we can get way off this curve. And that we understand very well. So what we really need is the details. First of all, how do we know what is the reflection of this globe? Obviously this cloud reflects less than this one here. There's a very elegant way we can do that. And that is looking at the moon. Now this is an almost new moon. You see, this is just sort of a nail here. And when the moon is almost new, it's actually, I think now, but now it's cloudy so you can't see it. You can actually see the full moon here. You can also see the backside of the moon. When you have a half moon and so on, this is much less easy to see. And there's a reason for that. When you have a new moon, if you were on the moon, how would Earth look? For a new moon, that would be a full Earth, right? Because here's the sun. I think this was taught in school as well. This is the Earth, right? If you have the moon here, it's a new moon, right? So you have sort of, it should be, let's put it there. It's a new moon, and over here, it's a full moon, right? So when we have a full moon, we have a new Earth standing on the moon, right? If we're on the Earth and look at the new moon, this is a full Earth, right? Which means that the Earth shines a lot. So what are we seeing here? That's Earth shine. This is Earth shine. This is sunshine, right? So that we could use, right? Because now we can compare. This is the reflection from the moon. Proportional to this, we don't know the reflection coefficient. What is happening here? This is, of course, what's reflected from the moon, goes into the Earth and is reflected by the Earth, right? So this is proportional to what's reflected from the Earth times what's reflected from the moon. This is just what's reflected from the moon. We don't care about the moon. But if we look at this color and compare to that color, you see the ratio gives a reflection of the Earth, right? So just look at this. How bright is this? How bright is that? And we get a measure of the full reflection from the Earth. That's a very elegant measurement that you do. So we can actually do these kind of things. Okay, now we want more details. Now we really want to know, what can climate do? Are we doing something serious about climate? Are we changing climate? How would we know that the fluctuations we see are not just natural fluctuations? How would we know? Well, of course we only know that if we would understand the natural fluctuations and say, now this is sort of what we would expect from natural fluctuations, and this is human-made, right? This is like, we have a dice, we're throwing a dice, and we don't know, we just throw it once, and it shows 7, right? Is this a tampered dice, or what is it? Well, we don't know, unless we know that we can throw dices, and they have to be in the range 1 to 6. Then we know we're outside this range. Of course, there are more sort of rigorous scientific ways of saying this. This is the kind of stuff we do. So the first thing is, of course, to see if we can calculate this. Can we calculate really what climate does from physical laws? And this has been tried, and this is being done. Well, I forget about that now. Okay. So how would you do that? We have the physical equations for the atmosphere. And what does that mean? That means we have things that we measure. We have the wind, we have the pressure, we have the temperature, and these things are related. The winds is just the motion of, we tend to like to call the air a fluid, of the fluid here. Now, this is moved because changes its movement because it's under the influence of some sort of forces. Forces in the atmosphere would be a pressure, right? I have a pressure from this side, I have a pressure from that side. If this pressure from this side is a little more than the pressure from this side, I'll move it in this direction. Which means that it's really the difference between pressures. So if we have a low pressure here and a high pressure there, we'll have the air being pushed from the high pressure to the low pressure. This is just Newton's laws for a fluid. Yeah. These equations were set up hundreds of years ago. That's the Navier-Stokes equation. But that's just the Newton's equation for fluids. Now there are some complications. We're really on a moving planet, so gravity keeps, of course, the air on the planet, but it has to turn, and we have some what we call fictitious forces, which would be centrifugal force, which will sort of throw you off the planet, and but then gravity is pulling, but it means that the Earth is not round, it's really flattened because it's rotating. And then there's another force which is sort of strange, which has to do if you move on the planet, if you move on a merry-go-round, you don't move in a straight line, you're curved. That's called the Coriolis force. All these forces have been put up. Now, we have equations for that now. Thing is, these equations, they're hard to solve. They're nonlinear, and which means that they're difficult to solve. But you say nonlinear, so, whoa, that's so hard. That's sort of the way you do it. So what can we do? We can try to solve them on a computer, which means that we don't have an exact solution. Now we say, oh, this is the solution to this equation. But what we can do is we can say, this time step, I know what the winds are here and there. And then I can sort of slice it up and say, in this blob here, I have the value of a pressure. In this blob, I have the value of a momentum or the wind. In this blob, I have the value of the pressure. In this blob, I have the value of the momentum. This wind here, there are some forces, which is the difference between the pressure here and the pressure there. So if I take the difference between this and that, this is how this one changes and so on. So I solved this numerically. This scheme was set up by a scientist, Richardson, who was actually he was a scientist, but he was, I think, called in World War I as an ambulance driver. And when he was not driving the ambulance, he would be doing this calculation. Say, I want to make a forecast here. I know what are the values now. And these were taken from different measurement stations around. This is Germany. And doing that, he wanted to calculate what would be the weather for the next 6 hours. Now, it took most of World War I. So, the forecast was sort of long gone. And this was published in 1922 or 4. And, of course, he could compare. What happened then in those 6 hours. And he failed miserably. Unfortunately, it wasn't a very good forecast that he did. But he was on the idea, and he said, the problem is probably that, I probably need to find what's called a grid for this in order to get things right and less approximate and what have you. So he envisaged a computer. So in 1920s, a computer, there was somebody hired who was good at computing. Right? So this is now a room of computers. So this is like a parallel computer. And all these guys are calculators. All these guys are calculators. And there's one director sitting there. And he's getting the calculation from there. It needs to be transferred over there. And he'll use his flashlight to do this and that. He needed 64,000 computers to do that. That was his vision. It never happened like that. But he was basically right. So what was needed was yet another war. Not for him to go and be an ambulance driver, but we needed World War II, which was a terrible war. But for physics, it was a phenomenal thing. Besides, of course, the atomic bomb, which I don't know if that was a phenomenal thing, but we had radar, and most importantly, we had the computer. And so the computer, which was made, to break the German codes, the ENIAC and so on. It was a huge boost to that technology. And after the war, there was this one guy sitting in Princeton with a big computer. And he was a genius, a mathematical genius. And he said, I want the most difficult problem in the world. Anybody know who this is? No. His name is John von Neumann. And he constructed this computer. He was really ahead of his time. And what was this? The most difficult problem for humankind. That would be making a weather forecast, doing what Richardson wanted to do. So he gathered a team of the best meteorologists at that time. And meteorology had also advanced during World War II. The Norwegians, they made the weather forecast for D-Day. I don't think they did it very well. There were some problems with, I don't remember the details there, but they would be doing it sort of empirically, you know, with fronts, and you know, we guessed that they would be moving this and that. So they had a whole school that made meteorology into sort of a semi-empirical science in a very clever way. But this guy wants to do it on a computer. We want to calculate. We want to do the physical equations on a computer and calculate that. So these guys, Jarny and other people that was the meteorologist from MIT came down, and they had this project going. This was in the early 50s. And they started out, and it turned out to be a hard problem. And on the way, a lot of interesting things happened, which I'll return to in a while. But I can tell you now that it was not until about 25 years later, in the 70s, that these guys could actually beat the Norwegians. Weather forecast is a good science in the sense that it can be tested. You know, it's not like cocktails. You know, does this really test well? Yeah, well, this is a good cocktail. You don't know. But you could say, is this a good weather forecast? There are a very specific way of doing that, and making a good weather forecast is not an easy task. If I say the weather tomorrow, maybe not today because we had snowflakes this size, but usually, on average, if I say the weather tomorrow will be as the weather today, and I make a bet, I'll win 70% of the time. Right? So a good weather forecast made on a computer should be better than right 70% of the time, right? So I have to compare to something, and the way of doing it is, of course, you know, you bet with the computer. Am I right or are you right? You know, who wins? So that's the way. And they didn't win over the Norwegian forecasters in another 25 years with that. That didn't happen until the 70s. But what they did discover on the way was that the equations showed some very strange things. Symbolically here, I would like him to have done an animation in Java or something like that. Yeah. Someday I'll do that. This is not a weather forecast. This is very symbolic, but this is a mathematical object that comes out of a weather forecast. So two meteorologists, Barry Salzman and Edward Lorenz at MIT in the 60s did the calculations. This was actually not for the weather, but for some simple fluid motion where you had heating and convection, and wrote down the equations for a lot of these grid points, or it was for waves, and then they cut down the set of equations to 8 different equations. And it turned out that they couldn't really get it to do the same every time. And so they would sort of started, and they had these sort of long stretches of computer, tapes, whatever, with little holes in them. And they just go on and drink some coffee, and they come back. And then it did something else than in the previous time they had coffee, so they had to restart it, and they went again and had more coffee. And, you know, I think they had a lot of coffee. And it didn't do the same every time. Now, this was a set of equations by Barry Salzman now, and he showed it to Ed Lorenz, and he cut it down to 3 equations. and got very, very famous on describing these three equations. Now, what this is showing here is really, you could imagine on these axes here, it's actually in 3 dimensions, but it doesn't really matter here, that you'd have, say, a temperature in this direction and a wind in that direction here. Now you start somewhere, like high wind, low temperature, and then you see what happens. Then the computer runs and runs and runs, and it runs and runs, and it will do something like that in time. And then suddenly it will do something like that. Now, if I had started it just a little bit differently, here, I have 2 trajectories, and it's actually what it is here. It's a red and a blue trajectory, and they would follow because they're very close, but suddenly they would sort of get apart, and suddenly one would be over here and the other one there. And so, you know, how would you know what's happening? Because I couldn't have sort of known the starting condition, the initial condition better than what I did there. So what Lorentz discovered was that this is a chaotic system. So this is really chaos. And it does something very strange. What it does is that what happens with time depends very critically on the initial condition. So the initial condition being exactly the same here, run for some while, and suddenly they go to either side. This is what's called for obvious reasons, the butterfly effect, because this is called the strange attractor. That's a whole different topic. That'll be some other time. But the analog is the flapping of the wing of a butterfly, which corresponds to that little tiny difference here, would eventually end up in 2 different situations. And I think I read somewhere else that it was actually a seagull that Lorentz has said, you know, the seagull flapping a wing over Brazil would change a storm, or not a storm, over the United States. But it has many sayings, and actually where the butterfly effect comes from really is a short story by Ray Bradbury. I think this is Sound of Thunder or something, where somebody moves back in time to hunt T-Rex, something like that. But he was told, you know, don't change anything, only shoot the ones that were just about to die. You know, shoots a T-Rex that, you know, right before a tree hits it or something like that. But turns out that when he comes back, that he had stepped on a butterfly, and that meant that, you know, English language was different and this and that. So that's the butterfly effect. And that was on the way on making a weather prediction. Okay. So what we know now is that, okay, if I start here, 2 initial conditions, I can run for a while, but here they will start to separate. And there's this time scale for that. And that is the fundamental time scale of predictability, which means that there's no chance that I can predict beyond that time scale. So I'll never be able to make a weather prediction that goes 3 months out in time. There would be a lot of money to earn if I could do that, but I cannot do that. That's impossible. So that's a fundamental result that came out of that. Now, so is there any hope for climate in that sense? I can do now weather forecast for a while, but weather is, as you know, what's that saying? Is that Mark Twain? Climate is what you expect. I mean, you wear short leaves, and weather is what you get. Suddenly it's snowing. So the weather is what's happening. So how can you imagine if you don't even know what weather will be in a week from now? How would you then say, how would the climate be, you know, this time next year? Is there any way you can do that? And this is 2 different things. This has to do with what kind of questions you're asking. If I'm asking, will April the 16th, 2011 be raining 10 o'clock in Copenhagen, or will it be sunshine 10 o'clock? I have no way of saying that. The analog is throwing a dice. I know if I throw the dice 1,000 times and calculate the average of my throw, I know pretty well that the average would be 3.5. And I even know with sort of 3.5 plus minus 0.01, depending on how many times I throw the dice. But it doesn't really help me in having the dice in my hand and saying what will happen when I throw this dice this one time. And that is the difference between weather and climate. That what we want to do is we want to predict the statistics, which means, is this 3.5? Is that changing with time? Is the mean going to be something else? Do I suddenly get, instead of 6, I can get a 7, so I can change, or the statistics is such that I get 5 or 6 more than I get 1 and 2, and so on. This is the science of climate change, and that's a hard problem, because all the weather is in there in order to do that, and a lot of things that we do not take into account with weather, we have to take into account when running a climate model, which is just a weather model run for a very long time, like throwing the dice many times and see what happens. Now what suddenly happens is that the temperature in the ocean can change and so on. When we do a weather forecast now, we just go and measure the ocean is this and that, and we run for a week, and the ocean temperature doesn't really change in a week. It doesn't matter. We just do that. Now, if we run for a year, of course, ocean temperature also changes. So we need to get that in. So we need all these things to be put into the climate model in some sense. And this has been the next 25 years since the beginning, since the 80s, where people started thinking we need to do this calculation, take the weather forecast model, make it into a climate model, and then do the calculation and see what happens. So this is sort of the history of computer power, I guess, for climate models. You do the same, exactly the same as Richardson did in 1922. Do it on the globe, not just on Germany. The first assessment report, which was 95, I guess, or was it earlier? I don't remember. So this is Europe. You barely see that. But if you get a little higher resolution here, you can see Scandinavia here. So this is the first assessment report, second assessment report, third assessment report. And then, of course, it should be fourth, but then the F was used. So now it's assessment report 4. They're very imaginative on acronyms and so on. And let's just compare now with Richardson's here. This is about the achievement of 2001. It's just about the same resolution that Richardson did in 1922. So these are, even though they're extremely complicated models, they are still very coarse-grained models for doing this kind of study. So, of course, what's interesting is this just statistics, or do something change from the causes of course, anthropogenic CO2, but also natural causes that comes from outside the climate system as such. For instance, volcanoes. So this is the present volcano on Iceland, and it shoots into the atmosphere a lot of dust, and that dust associates on this part as well, which means that this should be cooling the atmosphere. So we want to put this into the models again as well. Put these things in. Sun might be changing its output and so on. We want to put that into the models. And of course we want to put the extra amount of CO2 into the models. Now how well do they do that then? Let's just see. This is the measurement of the global temperature here, or the change from some mean through the last 25 years, 35 years here. And you see an increase. Now, this is of course very deceptive to the eye. Now, if I had put sort of a straight line here, you think, yeah, that's nice. Or straight. Actually, I could put a line like that in here. So you should be careful with these kind of things. They're extremely deceptive. Now, if you do note, now here, we had a big volcanic eruption here in 92. That was the Pinatubo. So this cooling here might have something to do with that, right? There's another one, I think, over here, or something like that. It's hard to say because you have a natural variability like that. And here you have something very strange. Why is there such a peak in 1998? That was a big blurb of warm water coming out of the Pacific. This is a big El Nino. It actually was so big that it influenced the whole global atmosphere temperature. So that's a part of a natural variability. It's not because there was more CO2 here, but of course, 1998, all the doomsdayers would say, you know, this is really, really going bad. Let's put all that into the models here and run the models. And now you see, suddenly in this curve, I didn't, this is from the IPCC report, the volcanoes. And just putting in straight lines like that would, I would almost say, decept your eyes to see that, oh yeah, there's a cooling, there's a cooling, there's a cooling. We understand that. Now, if you look at the observations, which is the black line, so just to set your eyes right, this peak is the same as that peak there. So this little bleep here is this Mount Pinatubo here, right? But we already have the idea that this has to go into the models. And this is just a knob that we turn in the models. Of course, we have to turn some knobs. So you see the models here, they're really good at doing that. Ah, there's a volcano, we put it in. Ah, there's a volcano, we put it in there. That's the red one here, right? So we can do that. Now if we put this one up with, and there's a long trend going up here, and that is the CO2. That's put into the models here. Here, this is the band of the models, but it's in there. We could now do the exercise of not putting in the CO2, but putting in all and everything else. You see what happens then. This is the same curve. Now it's smoothed a little bit. So this is the last part of it going up here. If we take out the CO2, this is what the models would do. Which means that this almost proves that carbon dioxide is doing the job. And this is the warming that we're seeing here. But you also see that we have problems here, that actually models with and without what we know comes in there has an unexpected warming here in the data, in the real data, in the observations that is not captured anyway. And you can split it between land and ocean, and this is something that has to do with the ocean there. There's a dynamics in the ocean that we are still not capable of resolving in the climate models as they are. So, what about then the things that we worry about, like storminess? Would there be more storms with changing climate? Now, these kind of things you've seen a lot, which is that now let's take an index of American hurricanes like Katrina and so on, and you see in average here, and there's an increase here going up there. Of course, that is might be alarming, and these things are published all the time. But if you actually take the record for the first part of the century, and a lot of these things have only been measured from here. Now, this is of course something I took because it's been measured back in time. You see that this trend here might very well be natural, And actually there's no physical basis for why should it be that the storminess should increase with increased greenhouse effect. So that is something that you have to be aware of. But there are lots of things we don't know yet in that. And I think I'm sort of way over time. So let me just end up with this one here. Now you cannot read it, and it's also in Danish, so I'll just read it out loud. So this guy asks, "Sir, did you lose anything?" "Well, yes, I lost my door key." "Did you lose it here?" "No, I lost it in the dark alley." So why are you looking here then?" "Well, here there's light." And that is how we have to do in science, right? We have to look under the light, and which means that if the question asked is out in the dark, we have to come up with an easier question that we can answer, and then we might increase the light out there. But just searching in the dark might not be the way to go. I think that would be all from me.
For some questions. So if someone has a question, please.
Sure.
Hey Peter, I know you. I have a question to the chaos model.
Yes.
So you said that because you cannot determine the initial starting conditions, you will always have this butterfly effect.
Yes.
But so couldn't you improve this model by being or by increasing this accuracy with the initial conditions?
Yes.
So is that what the weather models are doing by increasing?
It is actually not. Actually not. It could be. So what you're saying is that if we did more observations, now we are observing just in one point. Actually, we are doing less Earth-based observations. This is just economics, because satellites are taking over this and that. But the improvement is, in this case, really in the models. If we do a higher resolution in the models, even though the input is not getting better, we don't know better, that's enough for improving the forecasts. And I think for the sort of short times forecast, like forecasting the ash cloud out of Iceland, we have observations that are sufficient for that. And I mean, it would be, economically very expensive to increase that accuracy in the measurements a lot. Now the problem, just to be a little technical, what the problem is that you can imagine the error growth, the difference between true trajectory. You can imagine this is the true trajectory of the true weather. I don't know it, but I do a calculation, but I'm off a little bit. Now I can just look at the distance between my forecast and true weather, and that becomes large, and this is the error. Now I can, of course, improve, get closer, and my error will be less. So couldn't I just improve indefinitely? And the problem is that it's actually easy mathematically to show, I won't do that now, that the error grows exponentially. That's a very fundamental thing, that the error grows exponentially. Which means that if I want to say increase, double my precision, I need to increase my accuracy by no, how does that go now? I have to. How's the math now? Now it's late. In the cocktail bar, I couldn't do that. But you need exponentially good measurements for doing that, and that, of course, you cannot do. So you're sort of speeding up to catch the rabbit. The faster you run, the faster it will be running. So you cannot get there because it's an exponential growth.
I've seen some of these conspiracy sites on the internet where you can read that the weather on Earth is much more dependent on waves coming from the universe and changes in the sun.
Yeah. This is my friend Henrik Svensmark's theory that cosmic rays has an influence on formation of clouds. I mean, clouds are very poorly understood. The problem being that these are really microscopic processes. Making a cloud droplet and having it grow, say, to form rain and grow to form a cloud and so on is a microscopic process that depends on a lot of things. You need a nucleation site, an aerosol in the air, and this and that. And their theory is that if you have a charged particle, and this one charged from cosmic rays, it might work better as a nucleation, condensation nuclei, and this and that. And I would say it needs experimental verification to be sort of justified. I mean, I cannot rule out that there's an effect, but I don't see it as an alternative to the fact that greenhouse warming is there. Might be a small effect, but what we see, the increase in temperature is pretty well understood to be a result of increased greenhouse effect from CO2. So, and I don't see any reason to conspire against that unless you're part of the oil industry or you want to get in the newspapers or something like that.
Okay. So we'll stop here.
Another question. That's okay.
Okay.
On the one of the slides, you showed that the content of water vapor also had an influence
Yes.
in the greenhouse.
Yes.
Is there any measurements of that over time, or?
On the water vapor? There are measurements. The thing is, that's a very difficult thing because water vapor is a very integrated part of the process. So it goes like this, right?
Yeah.
Like the clouds, which is of course a part also of that hydrological cycle, right? There's a cloud, now there's not. So it goes in and out. So it is both a cause and an effect in the climate system here. And the last IPCC report reports the greenhouse effect of water vapor to be somewhere between, I think, 36 and 72%.
That's a lot.
Yeah, and the uncertainty is the size of the number, right? So that's a hard problem.
But you could imagine if the climate and the temperature raised a lot, maybe the amount of water vapor would explode and then somewhat keep it down, or I don't know.
Yeah, I mean there is a it's always that's a hard problem with feedbacks. Actually, the water vapor feedback it's positive in the sense that you imagine you start out with a very dry atmosphere and cold. Now it's being heated. Water is then evaporated out of the oceans into the atmosphere. Now water vapor is a greenhouse effect gas, which means that you get even more heating, even more water vapor in the atmosphere. So you get a runaway. Says then you could imagine that you would evaporate the whole ocean and get a 200 atmosphere pressure atmosphere like Venus, with like evaporated ocean. So why is that not happening? That's of course because something else sets in, which is that water vapor is then condensated into clouds that cool and rain out and do this and that. And you're always, of course, away from the runaway situation, because if you were in the runaway situation, you would suddenly go somewhere else because it's not stable. So, and in a stable situation, you have to do all the little details to see where exactly things are going. And that's, of course, a hard problem.
You could imagine that it will just start raining a lot, so you will never get a heating more than 5 degrees or 4 degrees.
Yeah.
And the rain will just.
Yeah, do it all for you. Yeah. It's. I mean, I think there. I mean, you have to do the hard calculation in order to see if it goes like that. Yeah. Yeah.
Okay, so let's thanks Peter again, and try.